So we're gonna start talking about polyphase circuits, or we won't say polyphase very long. We'll get into three-phase. Theoretically, what we do could be taken into 2 phases or 10 phases or something like that. But the vast majority of the circuits that you're going to deal with are 3-phase circuits. If you start looking at how power is transferred long distances or even around in your neighborhoods, most likely there's 3 conductors, and it is going to be 3-phase. If you look at industrial power, I mean, even like this building, anything that uses a significant amount of power in this building is going to be powered with 3-phase. So we're going to start to talk about that. And the analysis of this is not particularly difficult. When we get through all the definitions and the nomenclature and whatnot, we will usually end up with a very simple loop circuit, one source, a few inductors or capacitors, or some resistors, and very easy to analyze. But just like power, oftentimes the definitions and what's meant by this and what's meant by that is the difficult part. So I'd encourage you to really try and keep up on that. Well, if we look at a typical 3-phase system, and we'll look at several different deviations of this, but an easy system to think about is if I take this base, what I call is neutral, and I have 3 sources off of this. I'm going to say my first source is voltage A with respect to N, and that's going to be, I'll just take a magnitude of 120 at 0. It doesn't necessarily have to be 120, but that's a fairly common one. And then I'm going to put this next source here, voltage B, with respect to N, is 120 at minus 120, and we'll talk about whether that's plus or minus 120 on the angle there. And then finally, Cn would be 120 at minus 240, or would probably be more often expressed as 120 at positive 120, which those are, of course, the same thing. One thing about the units on here, in 3-phase, it's RMS unless stated otherwise. So even if we're talking in 3-phase, and even if we say voltage, it is inferred that it's volts RMS. Okay. So if we don't want it to be RMS, we will very specifically say it's not RMS. Otherwise, we'll take that as RMS in our 3-phase work. The other thing we're going to talk about is that the circuit is balanced. Okay, and there's some criteria for this being balanced. That is, the magnitudes of the voltage are the same. So the magnitude here, 120, the magnitude there, 120, the magnitude there is 120. They have to have the same magnitudes. Now in real life, are things balanced? Yeah, we try and keep them pretty well balanced. All of your circuits that we do in this class are going to be balanced because that makes the calculation a lot easier. Okay. In the real world, they might be slightly unbalanced. They definitely try to keep them from becoming significantly unbalanced. The angles. Angles are out by 120 degrees. So whether we subtract the angles or add the angles, they are 120 degrees between each of them. So if we take 360 and divide by 3, that should make sense. We've got 120 degrees between each of those angles, and I'll show those in a Phasor diagram pretty soon. And then the total impedance is the same. So if I put some load over here, I put some load there, I put some load there, the impedances have to be the same, because if the impedances weren't the same, then the currents wouldn't be the same, right? So if we start out with a balanced set of voltage, we should expect to get a balanced set of currents. If we have a balanced set of voltages and the impedances are the same, we have to get a balanced set of currents. So these are some of the stipulations for this being balanced. And even in real life situations, the systems are fairly close to balanced.
What does that say, the Z, the impedance?
Z total? Yeah, Z total there. Okay, so the total impedance for a particular branch, the A branch, the B branch, or the C branch, is the same. Yes?
I'm thinking back to what's allowed you have this term. I'm curious what physical implementation we can use to get a phase angle. Do we have different phase angles for those voltage sources? What is the component actually?
Well, if you to change the phase on a voltage, you could do that with a capacitor or inductor. A lot of times we do it in a practical sense with a capacitor. A lot of motors will have a capacitor. There'll be capacitor start or capacitor run, where you put a capacitor in to shift the signal so that you can get more torque out of it.
So we have that somewhere in the one of those.
These sources would be generated this way. We wouldn't start. I mean, we could, if we try and go from single phase and we want to produce three phase, we might try and do that. But most likely, this is going to be generated as three phase. So a three phase generator is physically built different than a single phase generator. Other questions? So, if I were to look at this in the time domain, I've written these in the phasor domain, but if I look at this in the time domain, I could say voltage AN in the time domain is 120 times the square root of 2, because remember that all of these are RMS values, and if I want the peak value, this is V sub m, the peak value, I'd have to multiply that by the square root of 2 because it's a sine or cosine wave. I'm going to assume 60 cycles here, 60 hertz. Okay, and the first one is at 0 phase shift. So if I do this for the others, the voltage, that wasn't too good there. So if I do this for the other, the voltage, let's say B sub n, in the time domain is going to be 120 times the square root of 2. Has to have the same magnitude. Cosine, 377t. Everything's going to have the same frequency that we're working with. I mean, we might start the next problem at 50 cycles or something else, but everything in this problem would all have the same frequency. What's our phase shift here? Minus 120 volts. And likewise, if I were to complete this, C to N in the time domain is equal to 120 times the square root of 2 times the cosine, 377t, then plus 120 or minus 240 would be exactly the same thing. And if you take these and you plot these, you're going to get something like that. Okay? And one of the things that we'll do down in lab, we'll break out some pretty old oscilloscopes. We have some 4-trace oscilloscopes, and we'll be able to put 3 traces up at the same time, and we'll be able to see all 3 phases at the same time, okay, which is kind of nice to see that this does exist and see what it looks like. Certainly for starting motors and whatnot, this is a lot better situation. If I go to start a motor at this point, or I look at any point in time, I have some significant potential differences there, don't I? I mean, if I look at single phase, and a lot of times our abbreviation, if I want to say 3 phase, I'll just say 3 phi. If you see someone writing 3 phi, that means 3 phase. So this would be 3 phase. If I look at single phase, what's single phase going to look like in time domain? It's going to look like that, right? And if I go to try and start a motor at this point, how much potential do I have there? Not much, right? Okay. So when I'm trying to get a lot of torque out of motors or start a motor, a 3-phase system is very attractive. Questions with that so far? We've got a lot of things as we're starting out to probably deal with. You may have some questions, and I'll try and address them as we go. If you look at your house, I assume most of you live in a normal house in a normal neighborhood, whatever that is. If you don't live on a cot in the back of an industrial setting or something, you probably live in a house that does not have 3-phase. It has what we would call single-phase power going to it. Although you could make an argument that it is actually 2-phase power. And this might be your typical house system here. And your author has this as an opening slide in Chapter 9, way back in Chapter 9 when we first started talking about AC. And this would be a typical house system where you have a 120 volt circuit here. You have a 120 volt circuit there. And then if you take the 2 of those, what are you going to have? 240, right? So you got some circuits here in the kitchen and the bathroom and whatnot. You got some circuits here in the garage and the living room and whatnot, just plug-ins. And then you go across both of those and you can run the dryer, the electric dryer, or the electric range, or something like that. So, I mean, technically, with what we've laid out, you could call this a 2-phase circuit. But suffice to say, you definitely do not have 3-phase in your house. Now, you probably have 3-phase in your neighborhood, and you might wonder, well, if I have 3-phase in my neighborhood, why don't I have 3-phase in my house? Well, what happens in your neighborhood is they bring in the 3 phases into your neighborhood, and probably you and the neighbor next to you are on 1 phase. and then the neighbor across the street and kitty corner down the way is on another phase, and then a couple houses down the street and across the street, they are on the third phase. Okay? And you might say, well, we don't all use the same power at the same time. Is that going to be balanced? Well, you got to remember, somewhere down the street there's a great big industrial application that uses way more power than all of you combined, and they help to keep it nice and in phase. Questions on that so far? So you definitely, don't have three-phase in your house. People get burnt on this all the time because they'll go to some industrial sale and they'll buy a really nice table saw and it's a super deal and they get it home and, oh, it's three-phase table saw. Okay, so probably not going to work, right? You're going to have to change the motor, or you're going to have a phase converter or something like that. So, which is probably worth talking about. Three-phase is a very efficient way to transfer power. You go out and you look at power, not necessarily just coming from the street into your house. That's going to be single phase. But if you start looking at power being transferred long distances down Lancaster or cross country, you always see how many wires? 3 wires, don't you? That's A phase, B phase, and C phase. So they're transferring it with 3 phase. Yes?
In the 2 small boxes, to the left, is that 120 degrees in each one?
120 volts. 120 volt circuit. So if you have a motor, and maybe there's lots and lots of different types of motors, so I'm going to paint with a pretty broad brush here, but if you go and look at the motor that's on a drill press or a table saw or something like you might have out in your home workshop or your garage or something, it probably has these bumps on it, and if it's maybe a big one on an air compressor or something, has lots of bumps on that. Have you seen those? Okay, those are usually the capacitors. And there might be, just for startup, sometimes they'll be on a centrifugal switch and you'll actually hear it as it gets up to a speed. You'll hear a switch go in or out, and it uses those for starting. Sometimes it'll use capacitors for running. We talk about starting capacitors and running capacitors. That is very indicative of a lot of single-phase motors. Okay. Now, you can have different types of motors. You can have single-phase motors without those, but when we talk about motors that have a lot of torque and we're going to put on an air compressor or a table saw or something with single-phase system, they're going to have those capacitors. Whereas a three-phase motor, it doesn't have those. So that's one real easy way to tell them apart. Yes?
So why is this such a big deal to have, why do you have the capacitors on the motors and stuff?
Yeah.
If it's such a quick frequency, 60 hertz, that's pretty fast.
Yeah. So like if we take this single-phase signal like this, a lot of times, and let's pretend they use this capacitor all the time, not just for startup, but if they use it all the time, they'll use that capacitor to shift this so now they have something like that, so they can get more torque out of it. Yeah. So that's the game on that deal. Another thing is just plain the motor size. If we look at single-phase motors, they are usually 3 to 5 horsepower and less. Okay. It is very uncommon to have a 5 horsepower single-phase motor. I've seen some rare cases where they're up to 15, but really, really uncommon. Okay. Whereas our 3-phase, usually it's greater than, more than 3 to 5 horsepower. If someone's running a 100 horsepower motor, I almost guarantee you it's going to be 3-phase. It's going to be 3-phase. So when we start talking about large industrial motors, it's going to be 3-phase. So that gives you some practical ideas there. Let's look at this in a Phasor diagram. And I think I said before, I kind of did the odd thing where I said that the B phase was minus. So I said that the A was 0. We said for this to be balanced. And I kind of went crazy here on writing this out. Remember, I'll put the PDFs up after class. So, but the A phase that has a magnitude at 0. And then the B and the C is going to have the same magnitude. And we said that B would be negative. Okay, and that seems kind of odd, but I'll show you why that works in a moment. And then C would be positive. Remember, that was minus 240 or positive 120. And if I put those on a Phasor diagram, this is just plotting them on the Phasor diagram. A real and imaginary. Real and the imaginary. I get something like that. And if we think of going from A to B to C, that sets up a rotation that is what? Clockwise? Okay. And a lot of times with three-phase, we're running motors, so oftentimes it is very much about the rotation. Okay. So if I have what I call an ABC sequence, which is a positive sequence, A is 0, B is minus 120, C is positive 120. Whereas if I have a negative sequence, I will call it an ACB or a negative sequence. People refer to them as both, ACB or a negative sequence. Again, they all have the same magnitude, but here I start A at 0, then B is the positive 120, and C is the negative. Okay? And that's what we call negative phase sequence. Well, if I put this on a phasor diagram, then B is up here and C is up here, and if I go around this thing, what's this? Counterclockwise, right? Okay, counterclockwise rather than clockwise. And that's one of the good things about three-phase and the bad things about three-phase. It is very easy to change the direction of something. Single-phase motors, sometimes you plain can't change the direction of that motor depending on how that motor is made. But with a three-phase motor, you can always change the direction of it, and sometimes it's way too easy. For instance, let me think about taking this positive phase sequence, ABC. So I'll write this down here, A, B, C, A, B, C, A, B, C, A, B, C. Did I get that right? A, B, C. Yep, good. Okay, so if you think about the phases, that's the order they're going to come in. Okay, from negative infinity to positive infinity. And if I switch any two of those, so let's say that I decide to switch the B's with the C's. So I'm going to have A, C, B, A, C, B, A, C, B, A, C, B. What have I done? I've gone from a clockwise rotation to a what? Counterclockwise rotation. Or like they say in England, what? Anti-clockwise? Whatever that is. I'm against clocks. Okay. So we'll see in laboratory next week that we can reverse the direction of rotation by simply switching any two of the, not necessarily letters down in laboratory, but any two of the leads. Here, by switching any two of the letters, which infers any two of the leads, I can change the direction. That's a good thing, right? I mean, I can get instant reverse. We go down to the machine shop over there and you tapping a hole, you get down to the bottom of the hole and you want to be able to get the tap back out and not break it off. You want to be able to instantly reverse that. That's great. Put a three-phase motor on that thing, you can reverse it instantly. What's that? A little bit, but it's not going to be instant. Okay. This can also be a bad thing because certain things like air compressors and pumps, they tend to only want to work in one direction. My brother's an HVAC engineer, got drug into a situation. He didn't do the initial design, but it was a customer or contractor they worked with a lot. They fought this system. Everyone was unhappy. Everyone was getting ready to go to court, and they asked him at the last-ditch thing to come in and, hey, can you check this out? Okay. Well, they were running the fan backwards. Okay? They'd hooked it up wrong. Reverse two leads, and away you go. Which can have a real problem. Some things don't like to spin in the reverse direction at all. People will start up equipment and it'll go in the wrong direction, and maybe the head will come off of it or something like that. If it's threaded on, it's definitely not designed to go in the opposite direction. So you have to really be careful of that direction. You can take something that's plugged in down in the shop here, and then we haul it across town and plug it into a plug-in over there, and we have to be real careful because it could go the wrong direction. So three-phase is very easy to change direction with. It's also almost too easy to change direction with. Questions with that? So that's what we mean by positive and negative phase sequence, and if you think in terms of it as a rotational sense about turning motors one way or the other, hopefully that makes sense. Well, we'll get into the practicalities of sources and loads and things like that. And we're going to have delta sources and loads, and we're going to have Y sources and loads. Okay? It could be in a delta configuration, so you have a delta. Or it could be in a Y configuration, where you'd have the Y. We still call it a Y if it's upside down. So if I take three sources, this would be my A, and then my B and my C. I've got three sources, and they are in a what? A Y. So this is a Y source. Okay. And usually we use lowercase letters for these sources. So you'll notice whenever I'm talking about the source, I'm using lowercase a, lowercase b, and lowercase c. Over here, I put some impedance. So this will be the generator impedance. Now if we look at a generator, doesn't it have windings in it? That's going to have resistance and inductance, right? So if we want to model that, we might put that generator impedance in there. And this is then, again, a Y source. We just put generator impedance in there. Sometimes that's a big deal and we want to put it in there. Sometimes it's pretty small. We don't worry about it. Then over here, we have a Y load. Okay, so these are our load impedances. Z for the load is right there. And there'll be three of those. There'll be one there, and there'll be one there. So those are all the impedances of load. And having said that, I almost never draw a Y load like that. I almost always draw it like that. Same thing, isn't it? It's a lot faster and easier to draw. So those are both Y loads. Then if we look down here at the delta, we have a delta source. And I guess before I leave the loads, you'll notice when I started talking about the loads, I changed to uppercase, capital A, capital B, and capital C with the loads. Then what if I have generator impedance in here? Should I put that in? Yep, I still have a delta source here. And finally, with the delta load, there's really only one way to draw it, so we'll just say this is the delta load. And the delta load, if I were to take these impedances here, just grab one of these and drag it down here, I don't want to do that because they're not the same. We'll see as we do the delta to Y conversion that that's not what we're going to want to do. The other thing that's probably worth noticing is I have this concurrent point here, this common point, what I'm going to call the neutral. So I'll call that with a lowercase n for the neutral there. I'd have that here, the neutral. I could even have that on this one, couldn't I? I'll give that capital N for the neutral. And it would be here, wouldn't it? That would be the neutral. Now there's actually not a neutral with a delta. And there's some things we do with a delta in terms of a leg that's a little bit different. I'll show you a slide of that next week in terms of some practical stuff. So usually we don't have that neutral with the delta, like they're drawn here. So let's say I put all of this together. I take maybe a Y source and put it together with a, isn't this a Y source? Yep. And I put it together with a Y load, and I get something like that. Okay. And over here I have the source. So I've got the whole deal here. I've got the internal voltage source. I've got the generator impedance in each one of the branches, in the A branch, and the B branch, and the C branch. Then I have the line here. Okay, we could have line impedance, right? So if this is our source, there might be some significant distance between our load, and we could have line losses there. So I'll say this is ZL for A, ZL for B, and ZL for C. We also have, because we've got a Y, we've got this neutral, and I don't know what to call a neutral, so I'll just say it's Z naught. It's probably not going to be a big deal, as you'll see in a little bit. Yes?
For line loss, do they have resistance like per foot per wire?
Uh-huh. Yeah. It's usually pretty small. Depends on also on how much current. Remember, it's kind of a vicious circle, because as you start to pull too much through it, it'll heat up, and as the temperature increases, the resistance will increase. So. Then over here, when we get to the load, I've got the load impedance here, and hopefully the generator impedance and the line impedance will be fairly small, almost trivial compared to the load impedance, because this is where we're wanting to do all the work. This is where we have the motor or the heater or something like that. So I'll have the impedance for A, for B, and for C. Now if I start out with these voltages being balanced, that is the magnitude of this voltage source and the magnitude of that voltage source and the magnitude of that voltage source, they all have the same magnitude, and they're separated by 120 degrees. That's one of the requirements for being balanced, right? The other requirements is that the impedance is the same. So I need to be able to say that the impedance for the generator for A plus the impedance for the line for A plus the load at A has to be equal to what? That is to say that this plus this plus this had better equal Z sub G for B plus Z sub L for B plus Z sub B, right? Better equal this plus that, right? And I guess for completeness sake, that had better be the same as what? Z sub G C plus Z sub L C plus Z sub C. Okay, so just because this impedance here isn't quite the same as that impedance there doesn't mean that it's not balanced. If you look at the sum, this plus this plus this, then that had better equal this plus this plus that. That's pretty common to make sure that those are all the same, but really we only need the branch to total out. Okay. Well, if all of this, we could call this Z for the branch. Okay. And I could say then that the currents, if I want to talk about the current, I'm going to talk about this as I little a big A. And maybe I'll talk about this as I little b big B. And maybe I'll talk about this as I little c big C. And what we're going to do is if it's balanced, so the voltages are balanced, they have the same magnitudes, and they're out by 120 degrees, and the impedances are all the same, we can draw the single-phase equivalent circuit, okay, which is going to look like this. So I'll have the internal voltage, I'll have the generator impedance there, GA, I'll have ZLA, and I'll have ZA. And I can essentially hook these together. Okay? And I'll draw it as a dotted line that's going from lowercase n to uppercase n. Okay. And this is what I'm going to call my single-phase equivalent circuit. Okay. Which makes finding this current a lot easier. If I talk about this as little a big A, that current I little a big A is going to be equal to what? Voltage A prime N divided by Z sub G for A plus Z sub L for A plus Z sub A, right? Now, if I were to think about B, if I were to draw this single-phase equivalent, and we don't usually draw it for B, we draw it for A, and any conclusions we get from A are a fairly easy extension to B, what's it going to be for B? Is it going to have the same magnitude? Absolutely. The only thing that would differ would be the angle, wouldn't it? Because everything is the same. The impedance is the same. The denominator is exactly the same. And the magnitude of the voltage is the same. The only thing that's different is the angle. So if I start out with a balanced set of voltages, my currents have to be balanced, don't they? Okay. So I could say that this would be equal to some magnitude of current at some phase shift theta. If this is some non-zero, or if it has some complex impedance, I'm going to have a phase shift there, right? And if we are let's say we're positive phase sequence, what is I little b big B going to be? Well, it's going to be the same magnitude, isn't it? And what's the angle? Theta minus 120. Okay, and then how about I little c big C? Same magnitude, angle, theta plus 120? Yeah. So usually what we do is we just come up with this single phase equivalent circuit. We solve for the A phase, and it is a very easy extension to get the B and the C phases. Now you might say, well what about, you glossed over this Z naught here. I didn't put that in there. Okay, well, I didn't really draw the neutral. I just drew this. I mean, theoretically, this does not exist. I just put this in because, I don't want to be accused of heresy on a Friday afternoon. This is an ugly way to go into the weekend, right? Okay, everyone likes to have a conductor there. It really doesn't exist, and it really doesn't matter, because if I take this number here, and this number here, and this number here, so if I look at I little a big A, and I add it to I little b big B, and I add it to I little c big C, what's that going to be? 0? I mean, let's look at the phasor diagram. We had the phasor for the voltage. The voltage phasor would look something like this. This is your A voltage. This was your B voltage, and this was your C voltage, right? And then the current one would just be shifted by theta. Let's say it's a positive shift, so I'll have something like this. So there's I little a big A, there's I little b big B, and there is I little c big C. When you add those up, what's it have to be? 0. Yeah, ideally, we're not going to have any current, not necessarily in this one, but in here, we are hoping that this current is equal to 0. And we'll see that done in laboratory. Okay, we'll have a three-phase system set up, and we'll do a rather extreme move. We'll just open this up. Just jerk the component out of there. That'll open that up. What do you think will happen? We'll start picking up a lot more current here, right? Okay. So because ideally this is pretty close to 0, I don't have to worry about this impedance, and it's pretty easy to come up with my single phase equivalent model there.
Why would it just be 0 when it's connected in the circuit? Like, thinking on the electrons, why would no electron just not go there?
Well, they all cancel each other out. Because, I mean, you could really think about this, again, I don't want to commit heresy here, but I mean, if we look at this as a vector diagram of forces way back in statics, and I say, what's the resultant force there, you'd say what? If they all have the same magnitude and they're out by 120 degrees, you'd say 0. Okay? Well, we're going to be getting to a situation where we have all kinds of possible combinations, where we might have, as far as the source goes and the load, we could have a Y driving a Y. That's what we got here, and it's very easy to get your single phase equivalent circuit, right? So that's what we would always like to get. Now, life's not always that way. Sometimes we have a Y driving a delta, and what am I going to do? Well, I'm probably going to try and change this delta into a Y, at least mathematically, to help me analyze it. Or we might have a delta driving a Y. What am I going to do with that? Well, I try and turn this delta into a Y, at least mathematically, to try and make the model easier. Because my goal is to get a YY, because it's very easy to analyze a YY. If I have a delta, sometimes you can analyze it like that, but a lot of times you try and convert the delta to a Y and the delta to a Y and analyze it as a YY, because the YY is pretty easy. I mean, if we started with this circuit, if I didn't have this silly dotted line and we had this solid line in here, that would have been an easy circuit on day one, wouldn't it? So like I said, probably the big difficulty in here is all the nomenclature. What do we mean by phase voltage? What do we mean by line voltage? And we haven't talked about those, but we're going to have to. The analysis part of it is not particularly difficult. Anyone come across the ferry, the Wheatland ferry? I don't know about the Canterbury, but well, I guess it's closed, isn't it, for high water? Yeah. If you look at the power that's being brought down to it, for a while it was diesel. I think they're back to electric. It's 3 phases. Why is 3 phases nice for that? Yeah, forward, reverse instantly. I mean, the people on one side it'd be kind of a bad deal if the ferry could only go one way, right? You have to tow it back somehow the other. Also, I don't know if you've been on the ferry, you notice as they move across, as they start getting close to the other side, what do? They reverse the props to slow it down. Okay. Another good example of 3-phase and even single-phase to 3-phase conversion is like a streetcar. It was a classic example historically of, I guess most streetcars have trucks like that. Do we have any train experts in here? Streetcar experts? Only models? Okay, yeah. So we've got something like that, which if you run the streetcar with just one wire above and, of course, ground below, that's kind of nice, right? You only have to string one wire. I mean, 3-phase, you have to have 3 separate wires, 3 sets of insulators, all of that, right? So we'd like to have a system where we only have single phase. So what we do is we'll have single phase here, and then once we get on board the streetcar, it was very common for them to have a single phase to a 3-phase converter. Why would we want to have 3-phase motors down in the wheels on the streetcar? So you can go back and forth, right? Okay. You probably noticed this with trains. I mean, the train has a big diesel engine. Is that hooked to the wheels? Not mechanically, right? It runs a generator and runs motors. And do you ever notice when they have trains coupled up, sometimes they're going forward, sometimes they're going in reverse? Train doesn't matter, does it? Yeah, over there.
So with a single phase, if you wanted to get the output to be reversed, you'd almost basically have to have a transfer case. It almost spins one way.
Well, you could do it mechanically, of course, with an idler gear. Absolutely. You can do it electrically, but it takes it's more complicated in the windings. Yeah. So, was there a question back over here? Yes. Yeah, the way the engines are, it doesn't matter whether the engine's going forward or reverse. It doesn't care. So they use a lot of this 3-phase technology in hybrids. In fact, the automotive area over there, if you walk past the big windows that they have looking over Sutter Drive, they've got a lot of components, and you'll notice, hey, it looks like there's 3 conductors in there. They're using 3-phase. Questions with that? Well, we will continue on from there next time.